Okay, so I just want to finish up the notes from where we left off. Actually, I'm going to redo D because I think I made a mistake based on someone pointing out to me. So remember that this is a product. So in order to actually find the derivative, we have to actually just distribute this all out, multiply. So we only know how to find the derivative of a sum, or therefore a difference. So, okay, anyway, so we distribute this out. We get 3x cubed minus 3x plus 3, and then minus x to the fifth plus x cubed. I think in class I said minus accidentally, and then minus x squared. And so we do have some like terms. We have a 3x cubed and another x cubed, so that's going to be 4x cubed. So we have negative x to the fifth plus 4x cubed minus x squared minus 3x and plus 3. So again, just as I said in class, make sure you're careful here. So far all we've done is algebra, so we haven't taken the derivative. Now when we go to take the derivative, we have our coefficient stays out front, the power rule, and then coefficient stays out front times, when I pull down the 3 for power rule, I'm going to have a 12x squared minus 2x minus 3, and then plus 0. And so we're done. So I think that corrects my mistake from in class. Now let's move over to E. Again, we're going to have to distribute this thing out. So y is going to be equal to x squared minus 1, when I do x times negative 1 over x, plus x, and then we do the 1 over x times everything. So that's going to be plus 1 minus 1 over x squared and plus 1 over x. Okay, so this we can think of, remember this piece is x to the negative 2, and this one is x to the negative 1. Sorry, I know my handwriting's not the best here, but I'm using a tablet, so. And then let's also just notice that the negative 1 and the positive 1 cancel. Okay, so when we go to take the derivative, we get 2x. That's gone. Then we have plus 1, which is the derivative of x. Now when I use power rule on here, the negative comes down, so I get plus 2x to the negative 3 and minus x to the negative 2. And so that's our derivatives. So again, the point with those was that we could take derivatives of things that look like they're more complicated, like products here or quotients, and we can still find the derivative. Okay, so now we just want to find the derivative of some new functions, right? So we know the derivatives of basic polynomials only. So we want to talk about the derivative of sine and cosine. Okay, so if somebody asks you to find the derivative of something and you don't have a rule for it, the only way to handle it is to actually try to use the definition, the derivative. So my function is going to be sine of x, and I need to just make sure I recognize that I know the definition of a derivative. So f prime of x is equal to the limit as delta x goes to 0 of my function, so sine of x plus delta x minus the function sine of x, and all of this is over delta x, right? That's the definition of the derivative. So if I actually try to evaluate this by direct substitution, if delta x goes to 0, I've got sine of x minus sine of x, which is 0 over 0. Now, so that's not helpful, but I do have this identity here that says that sine of something plus something is equal to this long mess here. So I want to apply that to where my theta is my x and my phi is my delta x. And the reason I'm doing that is I'm trying to simplify. So the only way I know how to simplify is to try to use some way to actually expand sine of x plus delta x. So this identity tells me how to do that. Okay, so this is going to be sine of x cosine of delta x plus sine of delta x cosine of x. And then I still have my minus sign here, so minus sine of x. And then all of this is over delta x. Okay, so now I'm trying to somehow deal with this big expression here. So if I'm careful about how I regroup my expressions, I can write this as, so there's a sine of x. I feel like I need my colors here, right? So I've got, oh, I don't know what just happened. Sorry. So I've got a sine of x here, and I've got a sine of x here. So what I'd like to do, let me go back to my ballpoint pen, is I want to factor the sine of x out of those two terms. So out of this term, I'm still left with a cosine of delta x. And out of this term, I'm just left with a negative 1. And both of those terms are still over a delta x, right? So I factored the sine of x, cosine delta x, that part over delta x. That's all this. And then the minus sine of x over delta x would be this minus 1. So notice if I distribute this sign back here, I have this term and this term, but I'm still left with this middle guy. So I have a cosine of x times a sine of delta x over delta x. Okay, now I grouped it specifically for this reason because in our previous packet, and I remember promising you guys that at some point we would use the theorems from chapter 1, packet 1, to actually find, we had these special limits. So this limit as delta x goes to 0 of sine of delta x minus 1 over delta x, that limit we actually found was equal to 0. So you can double check me by going back into packet 1. The variable wasn't delta x, it was x, I think, but the same thing is if you replace delta x with x, that's the limit we found. And then likewise over here, we found the limit in that first packet, that sine of x over x as x goes to 0, that limit goes to 1. So we're left with cosine of x times 1 here. So the part of the reason we did squeeze theorem and those limits that we spent that whole day talking about was for, so right here we have a pretty straightforward answer, I guess. And the point is, after all this work, the sine of x times 0 goes away, and so we're just left with, after all of that, cosine of x. And so the derivative of sine of x is cosine of x. So there you have it. And it took us a while to get there, and I certainly would never expect you to go through that on your own, but now that you know that fact, you can use it. So the derivative of sine is cosine. If it helps you, you should also be able to think about this from a graphical perspective. If I was looking at the sine function and I want to think about some key features that would help me justify that the derivative is cosine, let's make some observations. If I look at, let's say, at pi over 2, and I draw the slope of the tangent line, oops, pretend that I'm drawing that carefully. The slope of the tangent line is going to be 0 at pi halves, and it's going to be 0 also at 3 pi halves. So if I draw the derivative, I know the derivative has to be 0 at pi halves, and again at 0 at 3 pi halves. I know from 0 up to pi halves, it's going to be increasing, so that's a positive slope. So it has to be within the positive range here, but then it goes negative from in between those two values, and then it goes positive again. Now that's not enough justification, but it does give you just a graphical understanding. It makes the connection for you that yes, in fact, it makes sense that the derivative, the slope of the sine curve, actually gives you the cosine curve. And so that was pretty much what I wanted to get done in class today. And so we have these final two facts here, that the derivative of sine is cosine. So that one I proved for you. And then the one that I'm not going to prove for you, but is probably easy for you to believe, is that the derivative of cosine is negative sine. So that should be enough information for you to tackle homework 2. And please feel free to email me questions if you have any. And otherwise, I will see you guys next Wednesday.